Now, there are different types of rocket motors. For hobbyists, we generally use black powder motors, and those come in a variety of sizes. I'll set some of them out here. These are really, really small motors. I mean, this is a working model rocket motor. This flies in little rockets that we call Micromax motors, or Micromax rockets. They're about the size of my index finger. They'll fly to about 100 feet, but this is really, really small. But again, you can buy and fly these. You can go into something called 13 millimeter motors. These are black powder motors. These are going to be in slightly larger rockets. Probably the most common motor you're going to see is what we call an 18 millimeter motor, and this is 18 millimeters in diameter. So when you're talking about most model rocket motors that students are flying, they talk about A, B, and C motors. These are normally the size of motors that you would be flying. These are 18 millimeter. And then with black powder motors, we get into 24 millimeters. And these are going to be your D and E motors. So these are the black powder motors. Now, you heard me talk about, A, B, C, D, and E. What do those letters mean? And what it means is that every time we start out with a letter that designates it basically an impulse level or thrust level for that rocket, it kind of defines it into a class. So, but the important thing for you to remember is that every time you go up a letter, the total thrust of your rocket the total thrust of your motor doubles. So, a B motor is going to be twice as powerful as an A. A C motor is going to be twice as powerful as a B, 4 times more powerful than an A, and you double it every time you go up, to the point where the largest rocket motors we fly as amateur rocketeers are actually O motors. So I'm not going to do the math for you, but just go kind of figure out how many times more powerful an O motor is going to be than an A motor. So that's a little homework assignment you can do, and I think you'll be surprised. And those O motors get really, really large. So you get into what we get into called level 3 high power motors, M's and N's and O's. Those are normally 98 millimeters and in diameter, and those rocket motors can be taller than me. I mean, they can be 6 feet or more in length. So really, really large motors. Now, these are black powder motors. Now, when we start getting into those really, really large motors, we have to move away from black powder. We move into something that is called composite. And the composite is not made out of black powder, it's made out of something called ammonium perchlorate, or we call AP. Now, AP is the same fuel that NASA uses in the solid rocket boosters that went on the space shuttle. It's the same fuel they use in most of the solid rocket boosters they have on some of their other rockets. It's the same fuel that they're going to be using in the new Space Launch System that NASA is going to be flying later this year, and that's going to be the rocket that is going to be able to take astronauts back to the moon. Now, AP is very different in consistency. The black powder, when they're cast, so what you do is you take the gunpowder, the black powder, you kind of mix in like a little epoxy. It becomes kind of very like a slurry. It's kind of goopy, and then you compress it inside the cardboard tubing or the cardboard casing, and then when it dries, it becomes really, really hard and brittle. So, which is fine for the smaller rocket motors, but when you start getting into larger rocket motors, you don't want a hard, brittle propellant, because once you start getting into larger motors, it becomes really, really hard, very, very difficult for that propellant to be stable. It's really subject to cracking. If you happen to drop the motor, it can crack. You can get air gaps, which is not good, because when your propellant is burning, if you have an air gap, you're not going to get a consistent burn, and you'll end up with the rocket motor basically, we call it a CATO, but it's basically like a little mini explosion. So the motor casing doesn't explode, but all the hot gases, instead of coming out of the back of your rocket the way they're controlled, sometimes it goes on both sides. You have hot gases coming out the nozzle end, and then you have hot gases pushing out through the front end, and that's when your rocket is in flight, and that's not a good thing. That generally leads to bad results of your rocket. So black powder is good for the smaller motors. When we get into larger motors, we get into AP. AP is good because it has the same consistency as like a pencil eraser. It's very, very gummy. It's also a little more, we call it energetic. So it has a little more oomph for the amount of material that you have. It does burn a little bit slower, so it means your rocket motors will burn a little bit longer, which also helps to provide more thrust. But we generally don't put those in cardboard casings. We normally put them in either like a plastic or composite casing. Like this is a composite E motor. This is a composite F motor. And then for some of them, we actually get into motors that are reloadable. We can get all basically the parts of the rocket, and we can load our own motors, and we'll normally put those in aluminum casing like this. So this would be for basically, this is 29 and then a 38 millimeter. So this would be like for a G motor, this would be for an H motor. And then for some of our larger rockets, we get into 54 millimeter, and this would be like for a J or a K motor. So obviously much larger. And the rockets that we're flying are going to be obviously much larger that we're going to put these engines into. And again, once we get into the really large high power motors, the M's and the N's and the O's, those are the ones that are 98 millimeters in diameter. So almost twice the diameter of this engine, and 4 or 5 feet in length. And those rocket motors are generating thousands of pounds of thrust. So and the rockets we're flying generally can weigh dozens or sometimes even hundreds of pounds. So we're talking really large rockets. When you get to those size rockets, when you talk about high power rockets, you have to actually be certified to fly. So you have to go through testing and certification to be able to fly those. Most of the time you have to be over 18. However, for those of you that are watching, if you're age 14 or older, you can get your level 1 high power certification, which means that you could fly basically rockets that are using motors like this, a 38 millimeter high power motor. And if any of you have any questions on that, probably have my contact information. We actually have a club here in Dayton called Right Stuff Rocketeers, and I can kind of provide that information for any of you that might be interested in pursuing your level 1 certification. Next thing we're going to do is talk about how we keep our rockets stable. And this is important. For those of you that are actually going to go out and build and fly model rockets, you kind of need to learn the basics of stability. So 2 things you need to remember: center of gravity, CG, and center of pressure, CP. And the relationship between those two, because that's really important. Now, center of gravity is easy. Center of gravity is basically the balance point on my rocket. So I'm going to take this rocket over here. This is called the Land Viper. And so we're going to find my balance point on the rocket. So it's going to be right about here. And actually, if I have, this is without rocket motors. So we want to do this. You probably want to do it with the rocket motors loaded. But I'll just kind of use this to demonstrate. So that's my balance point. Center of gravity is right there. What that means is that the amount of mass on the front end of the rocket from that center of gravity is going to be the same as the mass or the weight on the back end of the rocket. So that's really easy to find. Now, center of pressure is a little more difficult. Center of pressure, if you were to go ahead and Google that or pull it up on Wikipedia, would tell you that that is at the midpoint on the rocket where all of the aerodynamic forces are the same. What does that mean? We talk about, all the forces on the rocket. So, for those of you that are wanting to fly, what does that really mean? Well, the easiest way to find that is to find out what's the midpoint of the surface area of your rocket. The surface area is going to be all this outer area on the nose cone, the body tube, the fins, taking into account, what is going to be the midpoint of that surface area. There are a lot of ways that we can do that. You can actually use geometry, and there are actually some good Estes technical reports that talk about how to do that. But we also have software that helps us to do that. But the key thing is it's going to be the midpoint on the surface area of the rocket. So my center of pressure is going to be that midpoint where the surface area on the back end of the rocket is going to be identical to the surface area of the front of the rocket. And the interesting thing is that when your rocket is flying, when your rocket is like this, you talk about this is your balance point. When the rocket is stable, whoops, is your center of gravity. But when your rocket is flying, the balance point on your rocket is not going to be the center of gravity. The balance point on your rocket is going to be the center of pressure. Now, why is center of gravity and center of pressure important? Well, the main thing you need to remember is you always want to have your center of gravity forward of your center of pressure. And what that does is that as your rocket, your center of pressure is here, your center of gravity is here. It means that as your rocket is flying through the air, it encounters a wind gust or something is changing in the air, and your rocket kind of gets knocked off center a little bit. if your rocket is stable, it will right itself and continue to fly straight. And the way that we do that is we normally say that if your center of gravity, the distance between your center of gravity and center of pressure is about equal to the diameter of your body tube, your rocket is going to be stable. So that's one of the things that we always try to do when we're building our rockets. And most kits that you buy will be designed so that you don't have to do a whole lot. They'll automatically be stable. But that's really, really important. One of the things I always tell students as they're flying their rockets, if you fly a rocket for the first time and you know that your fins are straight and you've built the rocket really, really well, but the rocket takes off the pad and it starts to tumble or it starts to corkscrew, that normally means that your center of gravity and center of pressure are way too close. The way you do that is you add a little bit of weight to the nose. You can do that with clay. Add weight to the nose cone, and I can guarantee you 95% of the time, 99% of the time, that'll fix the problem and your rocket will fly straight. So for those of you who go out and fly rockets, you build a brand new kit, it takes off the pad and it starts to corkscrew or tumble. Next time you fly it, add a little bit of weight to the nose and you'll be in good shape. All right, the last poster I have is going to be on the model rocket flight profile. And this relates directly to our model rocket engine. So I have my model rocket that's sitting on the pad. So it's sitting static. So we'll kind of put this over here. And I'm going to ignite my motor. And I use an electric ignition or electronic ignition system. And what we do is we take a little wire igniter, and it's kind of V-shaped. And that wire igniter is pushed up inside the engine nozzle. So it's pushing right up against the base of the engine at the propellant. As we run electrical current through that pinch point on that igniter gets very, very high because it generates resistance. It gets so hot that it actually glows red and will actually ignite the propellant. So our rocket is now leaving the launch pad and it's in the thrust phase, right? So our rocket's moving through the air, the engine propellant is burning. My rocket gets up to the coasting flight. So that means that now my rocket has burned through its propellant. It's now in the delay charge. So we talk about an object in motion will stay in motion, right? My rocket is now accelerated up. It's fighting the pull of drag and gravity. It's still going to continue up, right? Conservation of momentum. And it's going to get up to the point until drag and gravity are going to overcome its forward motion. And it gets at its highest point called apogee. And if the timing is right, at that point your ejection charge will go off. You see here it'll deploy your parachute and then your rocket comes back down safely to Earth so you can fly it again. And that's really important. We design our model rockets so they can be safely recovered. We do that for a couple reasons. One, and probably primary reason, is safety. If you were building a rocket that is not designed to be safely recovered, it's not a safe rocket and it should not be flying. The other thing is, model rockets sometimes can be, I mean, they're relatively inexpensive, but if you were to go ahead and basically build a rocket and then it would crash every time you flew it, that would become a very, very expensive hobby. So you really want to do that. So the fun is being able to go ahead and launch your rocket, especially if you put the time in, you really like that rocket, you want to see it come down safely because you want to fly it again. So that's where we put recovery systems in those rockets so that we can safely recover them and fly them again. All right, then the next thing I'm going to do is actually going to talk to you about the different types of rockets that we have. Because you see all these rockets that we have over on the table, I'm going to pull these up. The first rocket we have, and this is one that's going to fly on a little 18 millimeter motor. And this is called Fiesta. It's made by a company called Custom Rockets. And this is a good starter rocket. And there are a whole bunch of rockets that are like this, where you can start out. They're really, really simple to build. We call it 3 fins and a nose cone. You know, you go over and that's what this is, 3 fins and a nose cone. It'll take you probably maybe an hour to build, and it goes together with glue. You can put paint on it if you want, or you don't even have to paint it. And comes the plastic nose cone, so you know, you can glue it on one day and go out and fly it the next. Now this comes down by streamer rather than a parachute. Streamer works very much the same as a parachute, where you know you're trying to increase the drag on your rocket. The interesting thing is when your rocket is flying through the air, you want a low drag design. After your recovery system is deployed, you're now turning your rocket from a low drag configuration into a high drag configuration, because your rocket is moving through the air really, really quickly. to get as high and as fast as you can. You don't want your rocket coming down at that same speed, right? That's not going to be a good outcome for your rocket. So you want to try to slow your rocket down as much as possible when it's coming through the air. The way we do that is we increase the drag of the rocket. So we do that with a parachute, or we'll use it with a streamer, where this actually comes out, wind catches the streamer, and it slows your rocket down. So a lot of people ask, well, why do I use a streamer or do I use a parachute? It really depends upon the weight of your rocket. If your rocket is heavier, streamer's probably not going to work. The other thing is, if it's a little windy day, normally with rockets like this, you don't want to fly them in winds more than 10 miles per hour. You can fly them as high as 15. The National Association of Rocketry will only allow us to fly rockets, even the big ones, up to winds of 20 miles per hour. Anything beyond that, we're not allowed to fly. So if you're getting more toward 10 miles per hour, you may want to consider with a smaller rocket switching to a streamer. The streamer is going to allow your rocket to come down more vertically, and that means that it's still coming down at a safe speed. Your rocket won't be damaged when it lands, but it's not going to drift as far. Parachute is going to slow your rocket down even more, but if you have a good crosswind, obviously you're going to have to walk a lot farther to go retrieve your rocket. Or if you're flying in a field that's big enough to launch, but maybe you have some trees that are around the area, you may want to consider streamers, so to keep your rocket kind of landing more within the field. All right, next we'll talk about is a tumble recovery. Now again, most of our rockets you look at are kind of, they're very, very streamlined. Some of our rockets, actually for fun, we actually make them intentionally very high drag designs. So this is one that looks kind of like a flying saucer. This is a Semrock Jupiter B. And you can see it's not nice and streamlined, cone shaped, it's flat on the front. These are kind of fun rockets because you can put a pretty big motor into it. And it's not going to go very high, makes lots of noise, and it's going to land pretty close to where you launch. So what happens is when this goes up through the air, there's no streamer, no parachute. Basically, when the ejection charge goes off, it just blows hot gases out the top. But at that point, the rocket becomes relatively unstable, and it basically tumbles back to the ground. So it becomes a high drag design by basically creating a lot of drag by tumbling. And it's a very, very light rocket, so that'll go ahead and land. But this is a fun rocket to fly. We also have some rockets that come down like helicopters. And this is another rocket. This is a Semrock Gyrock. And as you can see, it looks like a rocket, but if you look very, very closely, the trailing edges on the fins have rubber bands, and they actually pivot. So this will fly like a rocket. When the ejection charge goes off, what it does is actually pushes out the engine mount. We call this the engine pod. And this gets pushed out, and this comes down by streamer. You can see the streamer that's wrapped there. And the rubber bands basically pull the trailing edges at angles, and now this basically comes down, spins very, very rapidly, and comes down, something we call helicopter recovery. So this is a little more advanced rocket to build, but for those of you, after you start building something like the Fiesta, you might want to consider something like this. With rockets, we also have kits that we call payloaders. And again, these are things that carry a payload. These are things we put in the rockets that we actually fly up to altitude. And so we have a payload section that's in here. This is kind of a clear plastic. It's kind of red in color. But this will basically push something up, and we can put electronics into it. This actually has a small little camera that we can put in. You can put altimeters. I've known some people that have actually gone in and they've, launched insects, and which are kind of fun. You don't want to put anything. You don't generally want to put anything in there more than an insect. NAR doesn't like you doing that. Don't put like small little animals in, but you can launch insects. There are a lot of people I know have done that as a science fair project, and gone into test the effects of rocket launches. But again, you can put all kind of different things in the payload, and this will come down by parachute. Next type of rocket we have is called a boost glider. So this is basically a rocket plane. So here's our rocket, here's our plane. So the rocket section provides the boost. You put the rocket motor in here, it goes up, flies like a rocket, flies vertically. When it gets up to apogee, the ejection charge goes off, nose cone comes off. There's actually a streamer in here. This part falls off, comes back down to earth. This now turns into a glider. And we've actually configured this so that when this comes back down, this makes nice slow circles and will come back down as a glider. So these are fun to fly. For a lot of people in rocketry, this is part of a big competition that we do called Boost Glide competitions. And I have fellow rocketeers that have competed, and they've built rockets similar to this, and their gliders have been in the air for 4 or 5 minutes or longer, which, if you think about it, that's a long time for these to be in the air, but these are a lot of fun to build. Okay, you had a chance to see the Land Viper previously. The one thing I didn't show you, that the Land Viper basically doesn't fly on one model rocket engine, it flies on 3. So this is called a cluster. So we have a cluster of multiple, basically when we talk about a cluster rocket, you have more than one motor. So what we would do is we would have 3 of these 18mm motors that would fit in here. And then we would go ahead and basically use kind of a modified set of clips that we would use so that we could go ahead and put in igniters and light all 3 rocket motors at the same time. Back before we had really, really large rocket motors like I showed you previously, when rocketeers wanted to go ahead and build rockets that had higher thrust, this is pretty much what you had to do. You ended up getting a higher thrust rocket by putting more rocket motors on the rocket. We now have the option, obviously, of just going with bigger motors. But these are still fun. These are challenging. I've known some folks that have, fellow rocketeers that have built really, really large models, and they have ignited as many as 30 or 32 motors at one time, which is actually quite a challenge. So, but again, these are also fun to fly. And again, these are things as you starting out in rocketry, you know, and you become more familiar with some of the basic rockets, then you can start going into cluster motors, and you kind of push yourself and you get into a little more complex designs and kind of increase your skill level in rocketry. We also have rockets that can fly on multi-stage, just like NASA has, right? You know, if you look at most of the NASA rockets, they don't have one single stage that'll get them up into orbit. They'll have multiple stages. This is actually a multi-stage rocket. It's called the Estes Checkmate. So it has a booster stage and it has an upper stage. So what we'll do is we'll actually put a booster rocket motor in the bottom, and then we'll put a regular model rocket motor in the top. The difference between a booster motor and an upper stage motor is that we don't have a delay charge or an ejection charge. We just have the propellant. So what happens is as this propellant burns through on this part of the booster that's connected to the other part of the rocket, when it burns through and it gets up to this point, it actually starts shooting sparks out the front. So, and then we'd have another motor connected on top of this, and those sparks, as they're shooting out the top, actually ignite the upper stage motor, which is here, and then this takes off, and then this basically falls away and tumbles back to Earth. So this is one way you can go ahead and build a rocket, and maybe without getting, you know, a more powerful motor, you can actually get your rocket to fly higher. And you can actually buy kits that have as many as 3 stages, some of them even 4. In rockets, we can also get into scale models. So these are going to be basically models of actual rockets. Now this is we'll call a semi-scale. It's not completely true to scale, but this is a semi-scale model of the NASA Space Launch System. And as I mentioned before, this is actually going to be the rocket that NASA is going to use to get back to the moon. Now the real one, obviously, is much, much larger than this. The actual NASA rocket is going to be, I think, 375, almost 400 feet tall. But this is a scale model that you can fly, and it flies on a single 18mm motor. These tend to be a little more challenging because as you're building scale models, you're trying to make them look as much like the real thing as possible. And there are some people I've known that are really, really good scale modelers, and they can build scale models that have so much detail that honestly, if you took a picture of the scale model, and if you took a picture of the real rocket, it would be really, really difficult to differentiate between the two because the scale modeling is that good. So this is a whole different level of skill. So for a lot of the kits I showed you previously, you're increasing your skill level in flying. A little bit in building, but in flying. But as you're focusing on scale modeling, you're increasing your skill level in actually building the rocket. And these are the things, if you like spending a lot of time doing a lot of fine touch up on painting and everything look just right, then you know, scale models might be something you'd be really interested in. Now, the interesting thing about rockets is I've talked about kits. You can also buy rockets that are ready to fly. We call them RTFs. And the ready to fly models are kind of like the Cessna Centurion. Basically, I purchased this. It came right out of the box. All I need to do is prep it. I put a rocket motor in. I go ahead and put some recovery wadding in with my parachute, take it out to the pad, and I'm ready to fly. So there are a number of kits that maybe if you're starting out in rockets or you're not sure, if you really want to start out and build a rocket first, you can go over and buy one that's ready to fly. And literally you take it out of the box, take it out to the pad, prep it, and you're ready to go. But this is an example one. And actually this does fly. This flies really, really well. It looks like a little fighter, which I like the design. Okay, I mentioned moving into larger rockets, and all the rockets that you see here that are flying on engines, basically A through D, are going to be low power. Once you start getting into larger motors, E, F, and G, you start getting into mid power. And so you're going to start flying rockets like this. This is a mid power rocket. This is called the Estes doorknob. This flies on a 29 millimeter motor. So basically it would be kind of like this F motor that I showed you. So that would basically slide in here and use this as an engine retainer, and you can go ahead and fly this. So as you start getting into larger rockets, you can do that. You do not need a certification to fly mid-power rockets. As long as your rocket it's flying on a motor below a G or lower, and it's not more than 3.3 pounds in weight, and this weighs probably just a little more than a pound, you can go ahead and fly it, and you don't need to be certified to go ahead and fly. Now, as we start moving up from mid-power, you could get into high-power rockets. And here's an example of a high-power rocket, and this is flown multiple times. This is made by a company called Lock Precision, and this is called the Athena. Here we go. And now this is actually flying on a 29 millimeter motor, but even with 29 millimeter motors, you can get really, really long motors. So this could fly on mid-power, but also high power. So this can fly on basically up to an H motor. And I've flown this with multiple motors of different sizes. But obviously it's much larger, it's much heavier. This is getting to the point right around 3 pounds. So, I could fly it borderline as a mid-power, but most of the time I fly it on high-power motors. This particular rocket on a high-power motor will fly probably up to about 1,500 feet. Now, I do have some kits. I've flown high power for a while. I have my level 2 certification, and which means I can fly up to high power on H and I motors, and then level 2, that's level 1. Level 2 would be J and K. So I actually do have rockets that I've flown up to that level. And those rockets, when you get up to level 2, they're normally flying up to around 5,000 feet or higher, and a lot of those rockets will come close to breaking the speed of sound. So, and then when you get up to level 3, those are going to be M and N and O rockets, and those are rockets that normally weigh dozens of pounds or more, and some of those rockets are going to be flying possibly 10,000, 15,000 feet or higher.